Right, what we want to talk about is the different types of lift. And we'll go through these. There are several types, and it's just based on the most basics of physics, and that's that's the three Newton's laws that we talk about. So we'll kind of start with that, and then I'll describe for you what types of lift exist, and then we'll go into how to kind of figure each of those and the physics behind them. And the punchline to all of this is when we get done, you're not going to have to know how to calculate each of those lifts. It turns out, as with a lot of things in engineering, what you're going to do is you're going to be given an equation with a coefficient of lift, and we'll deal with that. But you need to see what the different components are so that you can understand why different reactions of an airplane and different reactions from the pilot produce lift, or might cause us to lose lift in certain cases. Okay, so we have here the first of Newton's law is inertia. And inertia just says that a body in motion stays in motion until some external forces or the net external forces on it act on it to make it stop. It's hard for us to imagine this one because everything experiences friction in our world. The closest we could come would be a hockey puck or something that you would put on some ice and push it across. And the friction's relatively small, and it'll go a long, long distance until eventually the friction is enough to cause it to come to a stop. Doesn't typically happen very often. The second of Newton's laws is the F equals ma, force equals mass times acceleration. That is that if we want to accelerate a body, if we want to make a movement of something, then we have to do so by placing a net force on it to change its acceleration. Otherwise, it moves in constant velocity in the same direction. And then the final one is for every action, there's an equal and opposite reaction. And again, we can kind of understand this. If I were to run full speed down the hallway towards the wall at the end, I'm going to keep going at that same speed unless something causes me to stop. And that would be running into the wall. And hopefully you can see that both I exert a force on the wall, and the wall exerts the force back on me. If it didn't exert a force on me, I wouldn't stop. And therefore, I have to exert a force on the wall in that equal and opposite reaction. So, for example, the first type is deflection lift. Deflection lift is what we see when we bounce a ball. So you can see if I bounce the ball is going to hit the ground. There's a normal force that acts perpendicular to the ground that changes the direction of that ball. Now, if this is in a perfect system, in a vacuum, no friction and all that, then it actually keeps moving horizontally with the same velocity because we're not exerting any forces in the horizontal direction. But it does exert a force in the normal direction, normal to the plane of what it's bouncing off of, and that would cause it to deflect at exactly the same angle that it came in at, with the same horizontal velocity, but an equal vertical velocity, but opposite direction and turns it around. So we can do that. And what we're going to find is that this applies even to air particles. As improbable as that seems, when we move a wing through the air, we're pushing molecules of air out of the way that have to have forces exerted on them to push them out of the way. And they're going to exert forces back on the airplane wing that's going to cause the airplane to lift, hopefully to lift. Then the next one is the Bernoulli effect. The Bernoulli effect is, and you're familiar with this, you can change the pressure of fluid in a pipe by changing the diameter of the pipe. And the same thing is happening, although we're not in a pipe with aircraft, the same thing is happening with us. Essentially, whatever my velocity and pressure of my fluid that's moving through the pipe at this level is, as it approaches the narrowing in the Bernoulli with the Venturi, we call it. It's called a Venturi, which with two R's. Then the velocity goes up because the concept is I've got to have the same number of molecules that are accumulating here or coming in here have got to go through here. Otherwise, I start to build up and I have a balloon back here. So they've got to, especially if my pipe doesn't expand, then they've got to go through here And if the same quantity's got to go through a smaller space, they've got to speed up. As they speed up, the pressure drops, and we lower the pressure. And then, as things get through the pipe and get back out to the end and they spread out again into a little more normal flow pattern, the velocity drops back down and the pressure raises back up again. And that's what we call the Bernoulli effect that we use in aircraft. The next one is neat, and I'll do a demonstration of this in class. But it is the concept of, if I take a spoon and I have a stream of water running down, and I have the stream of water running down, of course it's going to hit the spoon and it's going to deflect off. But instead of either going on out at the angle of the deflection or dropping straight down once it clears, if you will, a vertical point on that spoon, it actually curves back. And it kind of goes this way, and it sort of keeps following the curve around. And that's called the Coanda effect. And it also affects airplane wings and the airflow around them. And it has some effect on how much lift we generate. And then the last one is the circulation effect. As wind circulates around an airfoil, we get different pockets of pressure, high and low pressure, and we generate lift in that way. And in any given airfoil, the total lift is a combination of all four of these in different situations, with a different airfoil, with different parameters and wind speed and angle of attack and all the stuff that we'll talk about. The different ones come into play differently. In other words, deflection is not always the most prominent form of lift. Bernoulli is not always the most prominent form of lift, depending on the characteristics of the aircraft. And like I said, we're going to go through this and explain what each of these are in more detail. But the good news is, take heart, you don't have to actually remember how to calculate all this stuff. As you get to it, we'll get to the end and we'll just put it all together. We'll put these in a wind tunnel and study those. Engineers put their wings into a wind tunnel and they study them, and they find out, based on a certain angle of attack and a certain wind speed, how much lift they can get generated from a certain wing. And it really is going to boil down to a function of the area of the airfoil and the velocity at which it's moving and with the angle of attack. And so we'll look at that and go through that. And so next I want to talk to you about deflection lift and how that works. So first one we want to look at is deflection lift. And deflection lift is just based on the fact that we are moving the particles of air out of the way with our airfoil, with our wing, as it moves through the air. Deflection lift is caused by the fact that the airfoil hits the air molecules and pushes them out of the way, and in return, those air molecules, in Newton's second law, exerts a force back onto my airfoil that we hope becomes lift. For example, if you had a thin airfoil in laminar flow, and laminar flow just means it's straight and even, and we draw it usually with nice straight lines like this. That's all that really means, but we like to work in laminar flow because the opposite of that is turbulent, and that's a really bad word to use in aerospace. But if I had a really thin airfoil, and I had my laminar flow here, what's going to happen is, for the most part, the air is just going to blow right over it. If you took your piece of paper in the activity that you just did, and if you could hold that piece of paper out, now most of you or somebody's going to say, no, it didn't, it reacted to my blowing. The reason is because the paper didn't hold straight out. It kind of limped down. You can't hold paper out straight. But if you had maybe a thin piece of balsa wood, same thing as if you take your hand and you hold it out the window with the car going down the road. If you can make it nice and straight, you don't experience a large amount of lift because the airflow is able to go over it relatively easily. If you then take that and turn it, what happens is we get this situation where the deflection lift comes into play. As the air molecules are racing towards my airfoil or my surface and they hit it, they're going to bounce off and they're going to deflect. The angle of deflection should be roughly equal to the angle with which it approached the surface. And the force that's generated on the air to make it deflect that way has to be normal to the surface. And then what we'll talk about in just a moment is that the air would exert that equal force in the opposite direction, normal to the surface, back on my airfoil. All right, so as the air particle, if you can think of it that way, collides with the wing, A force that's normal to the wing surface is exerted on the air to deflect it down and away from the wing, and resulting in a force pushing back. The air pushes back. On the wing.